Design Team 6 doing motor controller applications using the ECE480. I'm LT Thomas.
I'm Patrick O'Hara.
I'm TJ Valensky.
I'm Paul Aries.
We're going to go over the H-bridge and a simple speed controller. We're also going to talk about different
Can
types
you
of...
speak a little louder?
We're also going to talk about different types of motors and applications with TI. So there are two types of speed controllers, closed loop speed controller and open loop speed controller. The closed loops has some sort of feedback, so you can measure like the output and make corrections based on the output. How would you go about implementing a speed controller? Well, you need some type of protection. In our case, overcurrent protection. You need some switching mechanism because for a DC motor, like the way you control a DC motor is like you can control a DC motor by switching it on and off. So we need some sort of switching mechanism. We'll use an H-bridge, and an H-bridge can operate in a bipolar mode or a unipolar mode. We also need a pulse generator to generate the pulses. So this is the diagram of the motor controller. You can see here we have our overcurrent protection, our H-bridge, and a PWM pulse generator. You can have the PWM pulse generator can be analog electronics, or you can use a microcontroller, ECE480 in our case. So this is the H-bridge operating in unipolar mode. Basically how it works is that you turn these two transistors on and you have some voltage across the motor. Then you turn these two off and turn these two on and short it. And it corresponds to you get a high and you get a low. And then you turn these two back on, you get a high again. And you turn these two on, you get a short. So it's called unipolar because there's only the voltage is always positive as opposed to bipolar. The bipolar is a little bit different. You basically operate the opposite transistors. So these two transistors will be on, and these two transistors will be on. So the way it works is that you turn on these two transistors, there's an increase in voltage, and then you switch them. But when you switch them, the motor acts as an inductive load, so the current doesn't want to change like right away. So what will happen is that you'll have like a negative current flowing back through this transistor, and this is what you see here. So that's why you call it a bipolar, because you have like two different, the voltages will both positive and negative. This is a kind of application to a speed controller based on our diagram that we had before. This is the H-bridge, it kind of looks familiar. And the new stuff is the overcurrent protection. So the way it works is that this is a differential amplifier. So you sense the voltage drop across this resistor and feed it to a comparator where you have this V5 is some reference voltage. So if this output is greater than some threshold, you short these transistors to ground and basically shut off the PWM input to the H-bridge, protecting your circuit.
Okay. I'm LT Thomas, and there's two main types of polarity. There's axial and radial flux. What this means is for axial, on the height of the cylinder, we have two different poles, the north and the south, which is kind of uncommon for a motor. What's more common is the radial flux, which is the north and south polar on the base of the cylinder. So first I'll be talking about the stepper motor. This was introduced in the 1960s to replace servo motors and computer peripherals. So it's a cheaper way. How it works is this is a bipolar method. It can go both forward and backwards, clockwise and counterclockwise. We have two phases, A and B. So what this means is there's a series of teeth around here and a series of teeth. So it's teeth on the rotor, teeth on the stator. And what happens is there's one more tooth for every 100 degrees on the rotor. 180 degrees. So what this does is when there's teeth right here and teeth right here, when you turn phase A on, they're gonna wanna attract to the opposite, so teeth are gonna line up right here, and you're gonna have perfect alignment here, misalignment here. And then when you turn this off and turn B on, you're gonna need to move one full step, and that's one whole teeth going to the next teeth. So in this application, it'd be 100 or 1.8 degrees, and this allows for very, very smooth, not necessarily smooth movements, but very precise movements. And so the advantages to this are very long life because one, the rotor and the stator aren't touching each other, which means there's not going to be any mechanical wear. Also, it has excellent low speed because you're only moving one step at a time. You don't have to send it just a voltage and tell it to run. You're going to make it only go one step at a time every time. You also have high speed protection because once you start making it go too fast, the absolute worst that's going to happen is it's going to seize up and do nothing, but there's not going to be any mechanical wear on it. The disadvantages to it is it takes a lot of power to get it moving, and also the big size, you could have a much smaller motor and get the same amount of torque out of it. So, torque control. There's a lot of different things we can do with this. I just showed you how you can move it one step at a time. This is very inefficient. It's got low power consumption, but there's like no torque, and what you can see what's doing in the past was you're turning A phase on, A B phase on, doing it back and forth over and over again. But another thing you can do to get more torque is you can use both A and B phase at the same time. And what this does is you always have two phases on, which allows you to have a higher torque. Your resolution's still only one step, but you are consuming more power this way too. And what you can do to reduce power but still have high torque is you can alternate between having one phase on and two phases on. And what this does is you get a better resolution because instead of going the full step, you stop halfway in between, so you have twice as many steps now. You can actually go all the way up to an infinite amount of steps if you use pulse width modulation, and you'll eventually go like 1/32th of the way and keep going. This kind of shows like, if you're just doing one full step, you kind of get some overshoot and ringing. But if you're doing micro step, it's a lot more smoother, you get more torque, but the accuracy starts to get lost when you start to go to micro step because it's harder to predict each time there's a little bit of inaccuracy. So we wanted to decide which kind of motor controller we're going to use. How we do this, if you go on TI's site, you can go to applications. They'll bring up a schematic like this. They'll show you how to run low voltage and high voltage motors. This is just kind of the microcontroller stage, but what we want right here is the motor driver, which will be in the low voltage motor. Click on it, click PWM drivers, and we'll come up with this. So what we have here is a DRV88 X series, and these are a series of motor controllers that can also be used for stepper motors. We have all the H bridges that Coley was talking about earlier implemented here for the two-phase motor. All the controlling for doing full stepping, half stepping, quarter stepping, A stepping, and then the micro stepping stages. What's really great about this chip is if you're going to use a motor controller and you also need to have a microcontroller, you're going to have two different power supplies. But what you have here is you throw in your motor voltage that you need, and it spits out a 3.3 volt output. So you only really have to have one input if you're using this chip. This chip can do 8 to 45 volts and up to 2.5 amps. And I'll explain how to use these ports on the next slide. So here's just a simple implication of it. We just have the simple outs, 4 outputs, just go directly to the motor, control it. And what we have for our inputs are iSense, A and B. What this is you can detect the current you're actually pulling from each phase of the motor. You might want to do this if you realize there's a problem where you're pulling too much current, or you just want to monitor and try to keep a constant power consumption. A lot of people like to do this. Mode 0, 1, and 2. 0 is half stepping, 1 is 1/8 stepping, and 2 is 1/16, and you can mix them together to get up to 132. We have end fault. What's really nice about this chip is if you're pulling your temperature is getting too high, or your motor's not moving, but you're trying to tell it to, the end fault condition will go high. You can throw an LED to it, and it'll shine so you know that your motor's got a problem. You can also feed it back into the microcontroller and then handle that error also. We have a DAC. We're going to use this because you can control the amount of current you want the motor to pull if you want to have full current or use half current. Not a lot of people actually use it, but you do have control of it, so I'm just going to show it there. End reset and end sleep. This is end reset, put the motor back to its initial stage, and end sleep is just a sleeping mode if you don't want to turn it off. Direction, you can go clockwise or counterclockwise. All you do is send it to high and low. Real simple. All these right here, except for the DAC, are just straight up inputs, so they're really, really easy to implement with any microcontroller. And N-home is a really nice feature also, because what you can do with N-home is every time you make one complete rotation, it goes high for a pulse. So you're able to calculate your RPMs if you want. And next we'll be passing it off to Pat.